Okay, so our goal is to show that the rationals are dense in the real numbers. And this is me completing off a proof that I was supposed to do last time, but then, my computer exploded. So I'm basically going to start from the beginning. So let's begin by saying that we're going to choose an open interval. So let a be such an interval. Okay. Now the idea here, as I was trying to mention last time, let's look at such a candidate interval like this. There's our a, b. And what I want to do, obviously there are actually infinitely many rational numbers inside of this interval, but in order to pick one out, what we're going to do is we're going to choose a sufficiently large n so that if I move 1 over n places, if I just make all the ticks of size 1 over n, then I'm going to get something that looks like a cone, and the hope is that one of the tines live inside of this interval, right? So you can imagine something like this, and where this distance here is 1 over n. And if I just keep making those ticks, the idea is that eventually one of these ticks will live inside of the interval, and I'll have proven what I want to, right? Because that's what I'm trying to do. I'm trying to show that that this open interval contains a rational number. So in order to choose the 1 over n appropriately, I am going to say, let's let n be a natural number such that 1 over n is less than b minus a. And the reason I choose b minus a is because that's the width of the interval right here, like this, right? So by choosing 1 over n less than that, I can be guaranteed that as I walk down the real number line, marking off ticks 1 over n apart, one of these ticks is going to live inside of this interval. Okay, so that's my goal. All right, so now what we're going to do is we have to create the set where we walk down the number line, marking off the ticks at 1 over n. So let's define that. That's going to be called b. So define b to be the set m over n for m in z, right? And like I said, let me do this for the positive integers, but 0 is going to be in here, 1 over n, 2 over n, 3 over n, 4 over n, and so on and so forth as I walk down the number line, right? So the claim is that this intersects AB non-trivially. And that will actually, since b is clearly a subset of the rational numbers, if I have a non-trivial intersection with the interval AB, then I'm done, right? I'll have found a rational number inside of this interval. Okay, so to prove this, we're going to assume for the sake of contradiction that there is no such intersection, right? That the intersection between b and the open interval AB is actually empty. Okay, and what we're going to do then is we're going to say choose the largest integer which is less than a, right? The largest integer which makes m over n less than a. So let m be the largest integer such that m over n is less than a, right? So this is an element of our set big B here. If you're not convinced that such a set exists, you can continue by the completeness axiom, right? Basically take a subset of B, which are the collection of all those elements of B which are less than A. You now have a non-empty set which is bounded from above, and so voila, you can guarantee by the completeness axiom that supremum exists, and then you have to argue that, yeah, the supremum is in there. But let's not worry about all that. You can probably be convinced that such a thing is true, okay? Now, by the assumption that B intersect A, the interval AB is empty, this must tell us that m plus 1 over n is also bigger than B. M plus 1 over n must be bigger than b, because if it wasn't bigger than b, then it must be inside of the interval AB, right? And we would be done. So we are guaranteed that m plus 1 over n is bigger than b. But this is going to be our issue because, of course, the distance between capital M over capital N and capital M plus 1 over capital N is 1 over N, right? Which we said is less than the distance between AB. And now I'm saying that somehow it's bigger than AB. So these two things combined are going to give us our contradiction. And the way that we're actually going to write this out is we're going to say, well, look, B minus A, right? That is actually less than M plus 1 over N minus M over N, right? So here I've actually used these inequalities here. And then if I, they already have a common denominator, so if I put them together and simplify, that's going to give me 1 over N. But at the very beginning of the proof, we chose, 1 over N to be less than B minus A. And if we ignore everything in between here, we've now shown that B minus A is less than B minus A, right? And that's obviously false because 7 can't be less than 7 sort of thing. So this is a contradiction. And again, what were we trying to prove? So that tells us that B intersect AB is non-empty, and this gives us our rational point, which must live inside of this interval, and we're done.